Okay, good afternoon. This is the last session we are going to spend on these metric spaces, and then from the next time we go to the topic of sequences in metric spaces. But eventually, most of the time we will work with a set of real numbers. So I think the level will go down compared to what we have done so far in this part. Okay, so the theorems in this lesson is very technical, so I just want to make sure that you are not stressed. You just try to enjoy the flow of logic here. Okay? So no worries about it. And then what you need to know at the end is what the theorem tells you. Okay, not the proof of the theorem. So they're very technical sometimes. Okay. The first theorem is actually a very simple one, so you need to know that. Every compact subset of a metric space is automatically closed. Okay? So, this is 5.1. Again, the classroom notes are available. The numbers are identical, but the formats are different. Okay? So, what does this tells us? So we have a metric space X and D, and then what we know is that we have a compact subset of this metric space. So K is a subset of X, and we know that K is compact. The goal is to show that this compact is automatically closed. A very simple statement, and the proof is of course not very hard, but I think let us do the proof. But before do the proof, let me just recap. Can you just remind me what was the definition of a compact subset of a metric space? A subset is compact if every open cover of that K has a finite subcover contained in it. And that's not something very hard. So K is compact if every open cover, so do you remind me what is open cover? Every open cover, so let me write it curly U, O alpha in some index set A. Every open cover, so if you don't remember, it means that if you union all these O alphas, it will cover your set. It means that your set will be contained there. So that's the meaning of, this is the meaning of a cover, but when I say that open cover, it means that all these are what? Are open. So that's the meaning of open cover. So it covers and everything within it is open. So that's the meaning of open cover. So K is compact if every open cover U of K, so let me write the same thing here, of K, meaning this, contains, you remember, contains a finite subcover for K. That was our definition. So it means that if you have a cover for our set, you can throw most of it out. Only finitely many of them will do the job of covering your set. That's the meaning. If you have something like that, then you say that K is compact. Okay, now in this theorem, so let us do the proof here, or less rigorously. So what I know is that I am working in a metric space, and then I have a subset of that metric space. I know that that subset is compact. We want to show that it is closed. Okay. So if I want to show that a set is closed, what should I show? There are two things we can do. Both of them are good. The first one is the definition. So what's the definition?
That the complement is open.
Complement is open. But we also had one more theorem, if you remember, because in that case, I have to go out from my set and see that if the outside is open, then come back and say that my set is open, yes? But we also had one important result that I don't need to leave my set if I want to see that a set is closed, and that was it should contain all limit points. So it means K prime, the derived set of K, should be a subset of K. Both of them are good to remember. And by the way, I have added summaries. I don't know, have you seen that? So that summary is the information you really need. Okay? So proof. We want to go by definition, as you said. So I would say we prove that K complement is open. Okay? So I need to remind myself what was the meaning of being an open set. It means every point there is an interior point. So I would say let P belongs to K. We prove that. Can you complete it for me? We prove that what? P belongs to, it's an interior point. So it belongs to this. That's the goal. Okay? And if you want to do this, this is my advice for you, especially in analysis. I go to a scratch paper here. So a scratch paper. And I ask myself, if I want to prove this, what should I prove? I want to show that P is an interior point of a set. So what does it mean? Yes?
We have a neighborhood.
Yes, I can find a neighborhood of that point which is completely contained in my set. So this means that I have to convince myself that there exists an epsilon greater than 0, such that what happens? In the neighborhood with radius epsilon, center at P, okay, complete it for me. Is a subset of?
The complement, KC.
KC. Yeah. And that's what I want to show. So this is very good, you know. You have to learn this gymnastic. Then mathematics becomes not that hard that you can imagine, okay? So when I want to prove this, I go to a scratch paper, I ask myself, what should I do to prove this one? And I write something like this in front. And then my goal is clear. I want to go towards that, okay? But drawing a picture is also sometimes nice here. So let me see if we have enough room. So let me, in anticipation that this set is going to be closed, when I want to draw it, so let me contain the boundary in it, okay? So this is my set K. But where is this P? P belongs to KC, so it is outside. So if I want to draw a picture, might be we can put P here. So P is somewhere here. And I know my goal is to find a neighborhood around that which is contained in KC. KC means outside K. So I want to convince you about that. Okay, so how should I do that? What I will do, first I will pick a point from K. Okay, yes?
Why do we let P belong to K then? KC, right?
Yeah. Yes, this is correct. Thank you. Thank you very much. Yes. Yes, I wrote it wrong. Thank you very much. This is in PC. Yes, because I want to show that K to the C is open. KC is open. So I have to choose a point from my set and show it is interior. Thank you very much for the correction. Okay, now I would say that this part might be a little bit technical, but the flow, I hope that you can follow. Okay, so I would say let Q be in K, because somehow I want to use this information given to me. K is compact. I have to use it in some way. Okay, so I would say that let Q belongs to this one. So let me draw a picture for you. For example, let me choose a point Q in K. And then you see that these two have to be different. Yes, definitely Q is not P. Why? Because exactly as you corrected me, P belongs to KC, Q belongs to K. They cannot have any overlap, so they are different. When they are different, it means that the distance between them is not 0. Okay, so and I would say let, you might wonder a little bit, but you have to be patient. Let epsilon sub Q be defined to be 1/2 of this distance. Okay. So Q is here. I have this distance. This distance is definitely positive because they are not the same. And then I divide this distance by 2. Then what I will do, I will take this as the radius of 2 neighborhoods. One neighborhood centered at Q, one neighborhood centered at P. Okay. So in principle, what I will do, 1/2 is halfway. Okay. So I will draw a neighborhood around this point. What is the radius? The radius is epsilon sub Q. And what I do, I draw another circle, I mean neighborhood, not circle, okay? So around this with the same radius epsilon. Is that right? And of course, hopefully you see that there is no overlap between them because they are not containing the boundaries, okay? Okay, then the neighborhood, of course you should prove them rigorously, but I hope that this is not very hard for you. So then what happens, if I have this neighborhood intersected with this neighborhood, this is empty, yes? I would write it, prove it rigorously, okay? It's not hard. Imagine that there is an X there and try to find a contradiction. From the picture, it is very clear, and the proof is also proved, okay? Okay, now what I want to do, I want to make a cover for K, because I want to use somehow K is compact. This information is there, I want to use it somehow. But what I want you to feel is that I can change this Q and choose another one. Okay, and I can do the same thing. P is fixed, but there are a lot of Q's might be here. I want to do the same thing for every Q. Okay, for example, if this is another Q, what I will do, I will consider this length, divide this by 2, and draw another circle around that. Okay, so this is the middle, so this circle will be this one, but there will be another circle here as well, okay? So it's a mess, but we want to get some order out of this mess. So do you understand what is happening? P is fixed, and I choose any point that I like in K. For that Q, I define epsilon sub Q in this way, and I draw those two neighborhoods. They don't overlap. So then I go to another point, do the same thing. I go another point, do the same thing. All these yellow neighborhoods are centered at P with different radii. But these green ones can be in different places. And they touch the corresponding yellow neighborhood. Yes? Is that clear? So be careful. These green ones, they can be spread around. These yellow ones are all centered at the same point. They are concentric circles. Is that right? Okay, so now what we want to do, can you see a cover for K now? Yes, the cover is more or less clear, yes?
Yeah, it's all of the neighborhoods around Q, right?
Yes,
Yeah.
all the green ones.
Yes.
Yeah, so that's, you see, it's very easy to see. So I would say then, therefore, so let me define it in this way. N epsilon Q of Q, where Q belongs to K, is an open cover for what? For K. Do you agree with that? Why? Even rigorously, why that is correct? Because every green neighborhood contains at least one point from my K, and that is the center of that neighborhood. It contains a lot of other points from K, might be, but I don't care. It contains at least one point. And now I am running this Q all over K, and I am capturing all those green neighborhoods. So if I put all those neighborhoods on top of one another, definitely it will cover my original set. And why this? So it is a cover. Why it is an open cover? Because in the previous lesson we learned that every neighborhood is also open. So it's an open cover. Okay, but it is so. This is an open cover for K, and K is compact. It is mentioned in the problem. Okay, and K is compact. So what is the meaning? So it means that most of them are not needed even. Only a finitely many of them will do the job as the job is covering K. So this means that there are finitely, so hence U contains what? U contains a finite subcover for K. So what does it mean? It means that this K will be covered by a finitely many of them. For example, it will be covered by epsilon Q1. Let us imagine that there are n of them. Yes? Okay, so if I ask you, can you tell me what is epsilon Qi? What is epsilon Qi? Every epsilon sub q was half the distance from that q to p. So if I ask you what is epsilon Qi here, what do you say? It is half of the distance from Qi to that fixed p. And definitely this is also positive, yes? Okay, now can you imagine what do I need? Do you remember what I need? This is why it is useful. I need one epsilon, one positive number, so that the neighborhood with that radius around P will be completely outside of K. So for example, I cannot pick this yellow one because this yellow one is outside, but this yellow one is cutting it. Okay? I want to guarantee that there is one neighborhood around P with some appropriately chosen epsilon so that it is completely outside. And I hope that you can even simply guess that. What is that?
The smallest one.
No, because we don't know which one. In our picture, the first one was very.
No, I just mean the smallest one. I don't know which one it is.
Okay.
It is the smallest
exactly.
one. Of the
Yes, exactly. So we know that there are concentric circles.
Yeah.
One of them is the smallest one. Why? Because I have finitely many of them. If I had infinitely many of them, I cannot talk about the minimum of an infinite set. But I can talk about the minimum of a finite set. And that is extremely important. So now can you tell me what I should do? So you said that it's the simplest one. This is the intuition, and that's correct. But you want to write it in a mathematical form. So what do you say? I would say let epsilon, which I am looking for, let epsilon to be what? The smallest one.
Distance.
So the minimum of all those distances. The minimum of epsilon q1 up to epsilon qn. Do you agree this is a positive number? Yes, because all those numbers are positive, so that's also positive. The claim is that, okay, fix the claim. The claim is that n around p what with this radius is so I want to prove this. Is the picture clear? So we found the minimum one, and then we have some claim to work on, and then we start proving that this is a subset. But in order to prove this, I have to prove that this intersects nothing with K itself. Okay, so we prove that n p epsilon intersect K is empty. Do you agree that will be equivalent to that one? So we can say instead, we prove this. Okay, the best way to prove this is to use contradiction. Intuitively, it is clear. It is empty, and you are done. But if you want to do it, I would say let x belongs to n epsilon p intercept k. Yes? So then what happens? Then it means that x belongs to n epsilon p and x belongs to k. So then it means that x belongs to n epsilon p. So x belongs to k, but k itself is a subset of this union. If x is in k and we know k is a subset of this union, it means x is also in this union. If x is in this union, it means x belongs to at least one of them. Do you agree? So this means, and there exists an epsilon qi such that x also belongs to n epsilon qi of q. Yes? Okay, now what do I have? X belongs to n epsilon p. This means that the distance from x to p is less than epsilon. Do you agree? And then x belongs to this one as well. So x belongs to n epsilon qi. This means what? This means the distance from q to x is less than epsilon qi. Yes? So I am proving what was very obvious intuitively. But I told you in metric spaces, we always work with our Euclidean intuition, but we are not allowed to write it down just because our intuition works that way. We have to do the rigorous proof. Okay, so everyone agrees with what I have written here. So let me write this one number 1 and this one number 2 and try to add them. Okay, what I will do, I will say that let me add 1 and 2. What do I get? I get dx and p is plus d, if you don't mind, it doesn't matter, but let me write it the other way around, just for beauty. Yes. So q and x, and then plus d of x and p. If I start adding them side by side, the right-hand side will also be added. Yes? But do you agree with this one? Yes, because epsilon qi, I kept it the same, but I know epsilon is the minimum of this list. Then epsilon is less than this one. But then this means 2 times what? Epsilon qi. But epsilon qi is this guy, so I multiply it by 2. What happens? It becomes d qi and p. Yes? But where is the contradiction now?
Oh, it's the triangle one, right?
Oh, yes. Triangle inequality, because this one, on the other hand, should be greater than what? dqx plus dxp. It should be dq. I made a small mistake.
It should be xi. It should be qi.
This is qi, sorry. And that is also q1. That's also qi. Yes, if you see some mistakes, please just immediately tell me, okay? So qi, this is qi, sorry. Okay, let me wait a little bit. Yes? Yeah, that's correct. And you see the contradiction now, yes? Because this is the same number that appears there. So this number is less than or equal to this, but this one is strictly less than this one. This one is less than or equal to this one, that's equal to that one. So this means this number is strictly smaller than itself. And this cannot happen. Yes? So this means that, so this is a typical analysis proof. But from this perspective, it is easier than algebra because I drew some pictures for you. But in algebra, we cannot do anything. So I was thinking abstract algebra should be harder for you, but you're finding it the other way around. By the way, I talked to Christian, the examiner. He also told that, okay, whenever I taught this course, people had problems with analysis, not algebra. So I just want you to know that's the same feeling everyone had. Okay? Any questions here? So what you need to learn is that from now on, if I draw a compact set, I am not allowed to put dots around because every compact is automatically closed. Is that right? Okay. So we want to go to the next one. The next one is somehow a little bit, I mean, sometimes different. So what we have here, 5, 2. So what we want to do now, every closed subset of a compact set is compact. So in the previous one, we learned that compacts are closed. But this time, we want to learn that if I have a closed subset of a compact, somehow I want to tell closeds are compact. But that's not as easy as the previous case. In the previous case, every compact is closed. But in this case, if I have a closed subset of a compact set, then I can say that the set itself is also closed. So let me write it down here for you. And then I will go for a sketch of a proof. I don't want to write it formal because it takes a long time. So, and of course I have written it very carefully in the notes. So 5.2, this is telling me that I have a metric space. And then what do I have? I have F is a subset of, let me draw a picture from the very beginning, okay? So I have a set K, and you know that I have to draw it with the boundaries because it is compact. And then I have a subset within K, which I know is closed, so I keep the boundary exactly the same, but this one I know is closed. My goal is to show that F is compact. Yes? This is what we want to show. Okay, so a sketch of a proof. Okay, so again, tell me, I want to prove that a set is compact. What should I do? There's only one thing in my hand. What is that? The definition of compactness that you see the recap of the recall. Yes, I want to show that F is compact. So what I have to do, I have to assume that I have an open cover for F, and I want to guarantee that I can find a finite subcover of that. Yes. So what we should, we'll say that let U be equal to O alpha, alpha belongs to some index set, be an open cover. If you don't mind, let me write OC for open cover for F. We show that U contains a finite subcover for F. Yes? No, this is very good, by the way, because if you have to respect the definition. So if I want to prove that F is compact, I have to assume myself that I have an open cover for it and convince myself that I can always find it finite subcover. Okay, so let me guide you, because I don't want to prove it exactly, but you will understand that if you put my words with my writings, then it will be a formal proof, but we don't have time for it, okay? So what I want to say, imagine what I am doing here. So, I mean, all these yellow rays that I am bringing outside from F, can I call it something in mathematics? I just want to go outside F everywhere. What is it? What are these rays named? Outside F, I mean. I mean, if I want, it's a continuum around F. It's complement, yes? So what I can give it a name, the name is F complement. Is that right? But what type of set I am facing? It was given to me that F is closed, so its complement will be open. So F complement is open. Now let me ask you one thing, okay? I introduce a curly V this time, to be the curly U that I already had, but I want to append this F complement to it. Okay. Do you so what is this? Can you say something about this one now? So U was an open cover for this part. Okay? And now, because this is closed, FC is open. I am appending one element to this cover. Okay? Union them. Whatever set I had there, I still have. I append one more, and that is FC. Then I call this curly V. I hope that you agree that this V is an open cover. Do you agree it is still an open cover? Because whatever in U was open, this one by this assumption is open, so still this is an open cover, but open cover for? Okay. What is it covering? U was covering F, and FC is just this yellow part. If I put them on top of one another, it is guaranteed to cover K. It covers more or less everything. Yes, it covers everything, including K. So this means that, so this is why I'm saying that's a SketchUp proof. I'm not writing them. That is the oral way of saying them. So, is an open cover, okay, for K. Do you agree? But K is already given to be compact. So what does it mean? It means that, V, so therefore what? V contains a finite subcover for K because of what? Because K is compact. Yes? Yes?
That U should be K there.
What?
Alpha belongs to dot A, right?
No, it is in A. Alpha A is an index set.
X.
No, A.
What's A?
A is just a set. This is called an index family.
Okay.
When you say that I have an open cover, it means that I have a bunch of open sets. But how many of them are they? So I am naming them by an index set. That is the topic of index family of sets. In that way, so A is just an index set. So if you want, for example, one simple idea is to take A to be the set of natural numbers. Then you would have A1. But if I take it as a natural number, it means that I am granting that U has countably number of open sets in it. But there is no guarantee. I want to talk about all possible open covers, including the uncountable ones. Yes? Okay. So V contains a finite subcover for K. Okay? So what does it mean? So what can I say? I would say that K will be a subset of a finitely many of the sets here. For example, let me call it O1, union O2, union up to union On. So if I stop here, do you complain or not? Okay, so do you agree that this V is an open cover for K? Everyone agrees. K is compact. It means that K can be covered by finitely many elements of V. But if I write this, in principle, you have right to complain. Yes? Everyone understand what I'm saying? Yes? Why?
Because we don't know what n is. There could be an infinite amount.
No. This is compact. So it's a finite cover.
Okay.
We don't know n, but we know there is a finite number. Okay. And I am just trying to sell this to you, but you should be clever. This is not 100% correct. There might be another possibility, because what I am doing, I know V, which includes F to the C, is an open cover for K. And I know the whole thing has an open subcover. But when I wrote it down, I intentionally threw it out. So you don't know, might be FC should be involved in this finite one. Do you agree? Do you agree what I'm saying? So this means that in principle I should write also FC at the end. Yes? Because if I don't do that, it means somehow I know FC will not be involved in covering K. I don't know that. I know that V is an open cover for K, and I know that from totality, I can have only finitely many of them covering K. So there is no guarantee that FC is not there or it is there. It might be there or might not be there, okay? But if I add it to there, this is always true, yes? Do you agree with what I'm saying? Okay, but now, on the other hand, you know that F is a subset of K. So this means that I can add this one to it now. Yes? So F is a subset of the right-hand side. But just tell me, can I jump to the conclusion immediately without saying anything? I will say that, okay, I found my finite subcover for F. No? Why not?
But we can exclude FC because
Yeah, but because I want to find, we want to show that U contains a finite subcover for F. But FC is not in U, is in V. So this is a finite subcover for F, I agree. But this is not a finite subcover of U. But I can say that no, we are on the safe side. If this is true, then this one is also true. Do you agree? Because FC has no role in even covering one single point of F. So for K, there is no guarantee that I can drop FC. But for F, I can definitely drop FC. So then it means that O1 up to ON is a finite subcover of the original cover. And I am done. Is that right? Okay, so I feel that you are not happy. Okay, just ask me one question to see why you are not happy. You see, let me again. I want to prove that F is compact. I imagine U to be an open cover for F. And I want to grant that there are finitely many sets chosen from curly U that will cover my F. Yes? But up to here, I covered my F by these sets. But these sets are not all belonging to my curly U. These belong to my curly U, but this one does not belong to my curly U. Yes? But then I'm saying that if F is covered by these, it is guaranteed to be covered by the first n terms. Because FC means outside F. FC cannot cover even one single point from F because there is nothing in common. So if this one is true, I can safely drop the last one and still it is true. Understandable or not? Yes? Not happy again? Are you happy or not? Yeah. Okay, well. Okay, so this one is also good. So let us do one exercise. This is one type of exercise, for example, in the exam. This is very simple, by the way. F is a closed set, is a closed subset of a metric space X, and let K be a compact subset of X. Show that the intersection F and K is compact. So what does it mean? Let me write it down here, 5-3. So I have a closed set. So F closed, K compact. My goal is to show that the intersection is compact. This is what we want to prove. It's a very, very good exercise because it's more or less combines these two theorems with one result that hopefully you remember from the first lecture on metric spaces. So Okay, so K, so let me write solution. So K is closed, K is compact. The first theorem was what? Theorem 5.1 guarantees what? Do you remember?
Is closed.
K is closed. Do you agree? So we know K is closed. Now, F is closed and K is closed. Something we learned last time. What can I say about the intersection? There was a theorem that the intersection of any index family of closed set is closed, yes? So this is closed. Okay, I'll wait for you 1 minute, so finish the problem. The problem is finished now. Therefore, okay, now, you write one line and it's finished.
Since
F intersect, yes?
it's a closed subset of
A compact set.
compact.
Yeah, so what should I write? On the other hand, what can I write? F intersect K, even from simple set theory, you know what? It's always a subset of K. Okay? And then we are done because we learned that this is closed. We were given that this one is compact. So what can I conclude? I can conclude based on theorem 5.2 that F is compact. Yes? So that was a very simple application of these two theorems and one theorem we had before. So you see, this is nothing. So what I am saying is that, let us say that this was an exam question. You didn't know anything. You didn't need to know anything about the proofs. So you need to know how to use the theorems. Okay? Any questions? Okay, let us go to the next one. This is also a very important theorem, and it's a nice one. Yeah, we can finish this and then we stop for the break. So if E is an infinite subset, I should have written this in red because that phrase infinite is the most important part of it. So if E is an infinite subset of a compact set K, then E has a limit point in K. Okay? So theorem 5.4. So what do we have? So I have a compact set, and I am on the safe side. I can draw it very bold, yes? K is compact. And I know that I have a subset of this compact set, which is called E, but because nothing is said about E, let us consider the most general. I mean, it doesn't matter that much, so something like that. This is your E. But the only thing I know is that E contains infinitely many points in it. So E is infinite. Okay? So the claim is that K contains a limit point from E. So do you remember what was a limit point? What was a limit point? Yes?
Point on the. No, it wasn't. It wasn't a point on the border. It was a point.
Yeah, it's somehow not necessarily on the border. So I would say that.
On the border or inside.
So P belongs to E prime. Do you remember E prime is the derived set, is the collection of all limit points. If what happens, if and only if for every epsilon greater than 0, the neighborhood of radius epsilon around P contains an element from my set, but another different point from P. So it means for every epsilon, n P sub epsilon intersect with E minus P is not empty. That was the definition of a limit point. So a limit point is a point that if you draw any circle around that, no matter how small it is, it contains at least one point from the set which is not the center itself. Is that right? So for example, do you think that this one is a limit point? Yes, because if I draw this every circle around that point, it contains a point from my set which is not the center. Yes, in this case, this one. Do you think that this one is a limit point? Yes, because if I draw a circle around that, a neighborhood around that, it contains an element from my set which is not the center. Is this dotted line is also a limit point? Yes, because no matter how small I have the neighborhood around that, it will contain at least one point from E, which is not the center of the neighborhood. So that's the meaning of this. So if I want to show that K will contain at least one limit point for E. In other words, I want to show that E prime intersection K is not empty. E prime is the collection of all limit points, and I want to show that that collection and K itself have something in common. It means there is one limit point of my set which lives in K. That's what I want to show. But this phrase infiniteness is important. And the compactness is also important. Otherwise, we cannot guarantee these. Okay, do you have any idea what to do? So I would say that we can use contradiction, okay? So let's assume that E prime intersect K is empty. Okay, so let Q be an element. Let Q be an element in K. Okay. I think we should stop here and do it after, because I have to clean the board and I will be in trouble. So you can also rest a little bit, and then when I clean, I continue from here. Thank you.